In a previous video, we started talking about two-dimensional potential flows. We developed a Laplace's equation for velocity potential phi and also for stream function psi. Then we looked at several building blocks, very simple, solutions to Laplace's equation. Then we stitched them together to come up with the more complex solutions, such as Rankine's half body, Rankine's full body, flow over a circular cylinder, and flow over a lifting cylinder. So in this section, we extend it to something closer to our heart, which is a airfoil aerodynamics. Airfoils can be modeled exactly. That means apply the boundary conditions directly on the body surface. This is called the thick airfoil theory, or so-called panel method. This is what is used in many programs, including Xfoil. We will cover panel method in a later video. But today we are going to start with a very simplified version of it called the thin airfoil theory. So you would have already be familiar with the NACA series, 4-digit, 5-digit, and 6-digit airfoils, some naming conventions. In that particular lecture and video, we would have seen how chord line is defined as a straight line that joins the nose of an airfoil to the trailing edge. How to define the camber line with reference to the chord line. And then how to add thickness equally above and below normal to the camber line to combine and come up with an airfoil shape. In that lecture, we also saw that the angle of attack is simply the angle between the free stream velocity vector and the chord line. So this is usually given a symbol alpha. Sometimes you may have 0 alpha, but you would still get lift. That means even though the chord line is aligned with the free stream velocity, you get lift because the upper surface shape is different than the lower surface shape relative to the camber line and relative to the chord line. That means the airfoil is asymmetric. On the other hand, if the airfoil is symmetric, that means the above and below are same, like a NACA 0012 airfoil, then at 0 angle of attack is not going to produce any lift at all. We also showed some sketches of lift coefficient, drag coefficient, and pitching moment coefficient, how they vary with alpha. We talked about center of pressure, which is the point on the chord line where the pitching moment is 0. And we also talked about aerodynamic center, which is a point on the airfoil chord line. This theory says it's at the quarter chord line, where the pitching moment is not necessarily 0, Cm is not 0, but it's independent of alpha. That means the derivative of Cm with respect to alpha, which is the angle of attack, is 0. So we are going to look at how these things are quantified, how they are developed, is what we will be covering in this particular lecture. First of all, we want to see what happens when it starts an airfoil from time t equal to 0 in a wind tunnel, okay, or in a free stream. Then at time t equal to 0, it's got a 0 velocity. At time t plus delta t, where delta t is an infinitesimally small time increment, it's got a finite velocity v infinity. That means we have very abruptly started it, almost with infinite acceleration. This is sometimes called an impulsive start. So during those very brief instants in time between t and t plus delta t, lots of things happen, and the flow field around the airfoil continues to evolve. One of the first things we see is some of the vorticity on the boundary layer, both on the upper surface and lower surface. They grow and become thicker because vorticity tends to diffuse with viscosity. They get to be convected with the flow field. Remember, vorticity transport equation, things are convected with the velocity. So it gets dumped into the wake. So what you see is you find a very strong, clearly visible, strong vortex structure in the wake, which is spinning in the counterclockwise direction called gamma. So the circulation over the airfoil is equal and opposite in the circulation, because in the Kelvin's theorem, all these material particles were located around the airfoil at time t equal to 0. But at a later time, some of the particles have been dumped into the wake, other particles are still on the body. So if you think of a big box surrounding the airfoil, you have two vortex structures. One is the counterclockwise vortex in the wake, then a clockwise vortex in the airfoil. It's not a distinct vortex, it's a distributed boundary layer. So it's this clockwise circulation around this vortex that causes lift according to the Coda-Joukowsky theorem, which we saw earlier. So we are not rotating the airfoil, we are not doing any motion to it to produce circulation. Simply the vorticity, counterclockwise vorticity gets dumped into the wake, clockwise vorticity builds up around the airfoil. Together they add up to 0, therefore d gamma over dt, Kelvin's theorem, still holds. So initially the circulation is 0, later on the circulation is still 0. So this is a picture of it. So we are moving the airfoil from left to right impulsively. So when you do that, what happens is you generate clockwise vortices on the upper surface up to some point here. You produce counterclockwise vortices on the lower surface, and then also the flows seem to go around the trailing edge, so you get some counterclockwise vortices. Clockwise vortices means the flow is coming this way, counterclockwise means the flowing is coming in the opposite way. So somewhere here is a stagnation point in the upper surface. So you have a stagnation point near the leading edge, a stagnation point on the upper surface. Now the flow around the trailing edge has to go from low pressure to high pressure towards the stagnation point. Boundary layer does not like to go in what you call an adverse pressure gradient. That means the pressure is increasing. None of us want to go from a low pressure situation to a high pressure situation. So this fluid that is going from the trailing edge towards a stagnation point, it gets dumped into the wake, and it carries all the vortices, which are counterclockwise vortices that are at the upper surface between the trailing edge and the stagnation point, into the wake. So that's the counterclockwise vortex that you see. Now if you draw a big box surrounding the airfoil, this includes all the material particles, and circulation at time t equal to 0 plus, that means right after the impulsive start, is 0. So much later in time, if you still take the same box, including the same group of particles, still 0, except now we have a counterclockwise vortex, which we call a starting vortex. That means there must be a clockwise vorticity. It's not a single vortex, but it's a distributed vorticity structure on the upper surface and lower surface, the boundary layer. Does it mean the airfoil stops shedding vorticity in the wake? No. It continues to dump vorticity because the vorticity transport equation says any vorticity in the boundary layer here will continue to be convected into the flow, except the upper surface and lower surface from this point onwards are dumping equal amounts of clockwise vorticity and counterclockwise vorticity. Therefore, if you take a box here and draw a contour, there'll be net zero vorticity. So you have a counterclockwise vortex, clockwise vorticity surrounding the airfoil, and in the wake, you have an equal amount of vorticity above and below, including right at the trailing edge. So the picture that we could visualize is, this is the clockwise circulation surrounding the airfoil, gamma. We need to know what that strength of gamma is. We don't know yet. And then there is a starting vortex in the counterclockwise in the wake. So according to Coda-Joukowsky theorem, which we saw earlier, L prime is rho v infinity times gamma. We developed this for a lifting cylinder, but it works also for any situation where you have a vorticity over a lifting two-dimensional object, such as an airfoil. Prandtl was a German scientist. We will see his name many places. He used a water tunnel to visualize the flow. So this is an experimental visualization. He used some kind of particles in the water, so they flew with the water, so he could take a picture of it. High-speed photography for those times. This was between 1914, which is the First World War end, and 1930. Definitely before the Second World War start, which is the 1940s. So these pictures are grainy, but if you see here, you would see some kind of a flow around the trailing edge. You see a round circular thing at the trailing edge. So that's a starting vortex sitting on top of the trailing edge. Here it is being dumped into the wake, and it's moving a little bit down here somewhere. It's hard to visualize. It's up here in the wake. It's left the picture. Now we see just a smooth flow over the airfoil because the starting vortex has moved away, too far away from this picture. So in a wind tunnel coordinate system, the airfoil is steady. The fluid particles associated with the vortex move away from the airfoil roughly at the velocity of v infinity, because remember, convection is u times dO vorticity of dx. U is simply roughly equal to v infinity. So up here, this vortex is moving at the free stream velocity in a wind tunnel. In an airplane situation, this particle just stays put. The aerofoil moves away from it at a velocity of v infinity from left to right. So whether you do it in the wind tunnel coordinate system or in an aerofoil coordinate system where the aerofoil is moving, either way you get the same picture. So the total circulation of this big box surrounding the aerofoil and the starting vortex remains unchanged, because we are talking about the same group of particles enclosing the same group of particles. Therefore, the time derivative associated with this gamma is 0, d gamma dt is 0. This is what we previously called the Kelvin circulation theorem. So circulation around the closed curve that encloses the airfoil and also the starting vortex is 0. But after a long time, this box, the starting vortex is gone. We are dumping vorticity equal and opposite. So if you follow this airfoil, this circulation remains constant because we are dumping vorticity, but it's equal and opposite. So no new circulation is being generated in the wake. Therefore, no new vorticity is being built up on the airfoil either. Okay. Only time something would change is if you start pitching the airfoil up and down, or flap it up and down, change its angle of attack somehow, then the process of starting vortex repeats itself and new starting vortex will form, get dumped into the wake, and so forth. So this is another picture. This is before the starting vortex is shed. This is the stagnation point. Up to here, the flows are coming here. Here, the flow is coming this way. You can have two different velocities, finite velocities. So somewhere here, they go to 0. So this is a stagnation line. And the vorticity, starting vortex is now sitting on top of the airfoil, as shown in here. But much later, the flow has become very smooth near the trailing edge. Nothing is going around the trailing edge. By the way, in this picture, this is the stagnation point. Notice some streamlines are coming this way and they're going this way. These streams are coming here, they're going this way. So these particles are coming left to right. These are going from right to left. So somewhere here, 0 velocity. So that's a stagnation line, stagnation point, streamline. Here, there's no stagnation point at all except right at the leading edge. The particles come here, they come to almost a dead stop. Then some particles go to the left, some particles go to the right. Because the body is a streamline, velocity vector is tangent to it. So you cannot have a two velocity vector, one pointing this way and one pointing this way, unless the magnitude is 0. So at the stagnation point, the velocity is 0. So the pressure is the highest according to the Bernoulli equation. That's why when you run Airfoil or some other fluid dynamic software or Fluent, you'll get a very high pressure value. Here, CP, pressure coefficient, would be almost close to 1. You don't see any other stagnation point in this case in here. Okay. So this is initially at time t equal to 0. This is at a much later, after the starting vortex has left. Here the flow is going around the trailing edge. Here the flow seems to leave smoothly over the upper surface and lower surface of the trailing edge. So there was a scientist called Coda Same person from the Kutta-Joukowski theorem. He was a mathematician. He was in the same lab, same group as Prandtl. There were a lot of great scientists in Germany at the time. Kutta said that the flow at the trailing edge leaves the airfoil smoothly. He said that means he cannot have any pressure discontinuity above and below, because the flow will want to go from high pressure to low pressure one way. If you have high pressure on the lower surface, low pressure on the upper surface, flow will want to go around the trailing edge. On the other hand, if you have a higher pressure on the upper side and lower pressure on the lower side, flow will want to go around the trailing edge. Since nothing is going around the trailing edge, he argued the pressure above the trailing edge equal to pressure below the trailing edge. That means Bernoulli equation says the velocity magnitude above the trailing edge is below the trailing edge. Now we know there's a boundary layer over the airfoil. So when we say velocity magnitude, we are talking about the velocity field just outside the boundary layer edge on the trailing edge equals what's above is equals what's below, pressure above equal to pressure below, and the flow seems to leave smoothly. So this is called the Coda condition. Pressure above equal to pressure below. The flow is smoothly leaving the trailing edge. It's not wrapping around the trailing edge. And when we talk about velocity, we are not talking about right at the solid surface, because we have a boundary layer. We are talking about the velocity at the edge of the boundary layer. So this is called the Coda condition. So this is a mathematical picture of it. V1 equal to V2. It's not necessarily equal to 0. What would happen if the trailing edge had a finite angle? That means it had a finite included angle. Then the upper surface velocity will be coming one way, the lower surface will be coming the other way. The only way they could reach a trailing edge is if the trailing edge becomes a stagnation point. Therefore, if the trailing edge has a finite angle, the velocity magnitude would be 0. But if the trailing edge has got a 0 included angle, so-called cusped trailing edge, there's no reason for the velocity to be 0. They could be equal. They could be going this way. So we're going to stop at this point, stop this video, and we'll continue with some mathematical derivation in a subsequent video.